Hi, everyone. Hope everybody can hear me. We've got a great number of people registered today. I'd say just over 160, so thank you to everybody for joining us. Today I'm joined by, really excited to be joined by Dr. Stephanie Taylor. I met Stephanie a few times in the past down in Boston at the Healthcare Symposium, and Dr. Taylor's also been up in Toronto speaking to ASHRAE Toronto chapter. Today we're going to be talking about controlling respiratory infections through indoor humidity management. Couple of opening remarks. I'm very happy that there's a major event today not happening at the same time as our major event. There's a big SpaceX launch today, so hopefully a lot of you are going to be watching that later if work allows. We're also going to have a couple of handouts for you, and we had a poll at the beginning, so look at the handouts section. And as well, the first poll was about whether you humidify your home, and it was interesting to see about 50% of you did that. So hopefully we can, after today, get that up for next winter. So a little bit on Condair. Condair is the world's leader of commercial and industrial humidification and evaporative cooling products, and they've been so for over 65 years. More recently, Nortech Humidifiers has changed its name to Condair because they're such a big company with different brands all over the world. They wanted to have one global brand. So there's no change to the company, just a name change for us here in North America. Personally proud. I've always been excited to tell people that the engineering competence is right here in Ottawa, Ontario. In fact, we're manufacturing, or Condair is manufacturing humidifiers in Ontario and shipping them to the rest of the world in Europe. A little bit on Kilmer Environmental, for those that don't know. Obviously, I'm Glenn Kilmer. My partner is Ed Carney, and Ed and I took over the business about 10 years ago from my dad, Tom Kilmer. And Tom started the business in 1987. And we are essentially a manufacturer's agent, so we represent a bunch of different manufacturers. Most recent manufacturers that we've taken on that we're excited about are Aon and Rux Engineering. Today, our star of our show is actually Dr. Taylor, not myself, so I'm going to pass it over to Dr. Taylor in a second. But for anybody who hasn't heard from Dr. Taylor before, she's a graduate of Harvard Medical School and has a master's in architecture, and close to home for me, as a past president of Toronto chapter of ASHRAE, Dr. Taylor is also a distinguished lecturer, and we've had her here in Toronto recently, as well as I think the Hamilton chapter. So as I pass the show on to Dr. Taylor, I'd like to leave you with the definition of air conditioning, and it has always included humidity. You've got to remember that humidity, both on the high and the low end, is part of the definition of air conditioning a space. So I'm going to pass it over to my friend, Dr. Taylor, for her part of the presentation.
Hi, Glenn, and thank you so much for inviting me here. The Toronto meeting was one of my very favorites, and not just because you gave me that beautiful red sweatshirt, but you have a great group.
Thank you.
And I'm always impressed when a father-son or parent-child team works together. I think that shows a really good relationship. Speaking of which, that's my wonderful son,
Nice.
Colin. An emergency room physician, and I worry about him every day. But let's get started. So I'm also on the ASHRAE Epidemic Task Force, which is a six voting person group, and we've been working to come up with guidelines that are consistent with the CDC and the World Health Organization around how to manage buildings. So in this time of reoccupation. So it's been a really exciting, disruptive but exciting time. So to get started, how do we control respiratory infections with indoor humidity? I'm happy to be with you, and I wish I were there in person with my little dog Luigi, but we're in my office and happy to be here. So I want to talk about these three things. How this pandemic has really rearranged or at least highlighted some different priorities for buildings. And then I want to show you some studies on human beings indoors, and then resolve a few misconceptions and set the scene about where we go with this information. So to get started, how did I as a pediatric oncologist come to be here? So when I was in medical school around 1983, I decided I wanted to go on an adventure. So I went to Papua New Guinea and practiced medicine for 4 months. It was really amazing, a lot of fun. That was my vehicle there on the right, that dugout canoe, and I slept in villages when I wasn't stationed in this main hospital in Wewak. And you can see in this hospital, the conditions are different from what we see in North America, Canada, and the US. Families stayed in the beds often to help with the patients. The middle, you see a men's tuberculosis ward. And on the right, you see me looking sort of surprised at this patient who had elephantiasis. But, you know, I'm wearing flip-flops, which was the normal footwear for the operating room, and the surgical nurse didn't have gloves on. And I show you these pictures because in retrospect, looking back, I thought to myself, why is it that these patients didn't get new infections from the hospital? They didn't get MRSA or flesh-eating bacteria. So just keep that question in your mind. And remember that Papua New Guinea is a little bit north of Australia, right around the equator. So in thinking about that, I thought, well, maybe that was so long ago, there was no such thing as a nosocomial infection. But in fact, they've been around for a long time. And in this country, going into the hospital is like the third or fourth leading cause of death. Many people go into the hospital and get an infection from the environment. And this trend is what, as a physician, got me looking at the building, because I thought that there was the building and the built environment had some role in these infections. So you can see that the gentleman on the left was the dean of my son's medical school, Dartmouth. He had a ski injury, tore his meniscus, went in to have a one-day procedure, came out 4 months later, almost without his life, but definitely without his leg from a MRSA infection. The little girl in the middle was one of my pediatric oncology patients, survived her leukemia, survived her chemotherapy, and almost died from an infection. And in fact, we don't really know exactly how bad this problem is. It's pretty bad, and it's hard to get good data, at least in the US. But nevertheless, why is it that in these fancy hygienic hospitals, this is a problem, and yet in Papua New Guinea, it was really not a problem? So in thinking about this, I remember, again, this is my mentor when I was in medical school, wonderful guy, and we were doing cancer research together and using mice. And one night around 10:30, 11 o'clock, I went in to administer the treatment, and a lot of our mice had died. And I called Dr. Folkman, and I was like, I don't know what's going on, but something's going on. He came in from his house in the middle of the night, and we scrubbed the lab operating room down from top to bottom. And he said, never, ever underestimate the power of the environment in clinical outcomes, whether you're a mouse or a human being, whether you're a patient in a hospital or an employee in a business or a student in a school, or all of us in our homes. The environment is really powerful in shaping our health. So speaking of the environment, you know, if you look at our dwellings over time, starting from thousands of years ago, when we lived in caves or in shelters that were usually natural, they had a lot of communication, air, water, soil, plants, animals. And then as human beings, we became more and more sophisticated in our ability to manipulate our environment. By the Industrial Revolution, unless you were a farmer, you probably worked indoors, you know, with electricity, heating, sanitation. And now many of us work in sealed buildings that are very comfortable. You can go to work in a t-shirt if you're allowed to. They're often sealed with a lot of recirculated, filtered air. So as we've advanced our building technology, unfortunately, we've also seen a rise in infectious diseases. And not just infectious diseases, but inflammatory, autoimmune disorders, allergies. So while this isn't a statistical analysis, it bears asking, is there really a relationship between how we manage our buildings and an increase in these diseases? And of course, right now, we're all dealing with COVID-19, disease caused by the SARS-CoV-2 virus. The thing that's really interesting about this virus is that it's part of the coronavirus family, which is an RNA virus, meaning that the genetic material that guides replication is RNA versus DNA in humans. The thing about RNA viruses is that when they replicate, they make a lot of mistakes. And they don't have the proofreading repair mechanisms that, for example, DNA organisms have. So why does this matter? Well, it matters because if one of these mutations, of which there are many, sets up residents in an environment that was previously inhospitable to the coronavirus, then it doesn't have any competition. And not only does it have a place to live, if it finds a host, such as a human being, that doesn't have any immunological memory to this strain, then not only does it have a new environment to take over, but it also has a new host. And this is what we're seeing with this SARS-CoV-2. So again, are we doing something indoors that could be creating an environment for this new virus? And if so, what can we do about that? So let's take a look at some studies that ask the question, how might the building influence human health? So think about how you would set up such a study. I mean, it's easy to say, how does a building envelope relate to energy consumption? Because we have an energy meter. So in thinking about how human beings do indoors, we have to think about the human being being like the biomarker for the building. Because really, if you think about why do we have buildings, yes, they're to protect us from the rain and the snow and floods. Yes, we want them to be energy efficient, and we don't want to contribute to, greenhouse gases and things that Elon Musk is working on even today. But we really need to focus on the third thread of a building's purpose, which is how do we protect occupant health? So I really like this video. Glenn, you've seen it before. As I'm talking, actually, there are two copies of it. Hang on one sec. Oh, well. So as I'm talking, droplets come out about 100 microns in diameter, carrying all of the bacteria and viruses and fungal organisms in my mouth and nose. And these are normal. We all have them. As this engineer works away on her drawings, you can see she's leaving skin flakes on the paper on the desk. Those skin flakes carry Staph aureus, the normal bacteria for human skin, and a lot of other organisms. Those things coming out of her nose are not boogers. Those are normal particles that we exhale. And if you can see her GI tract is illuminated. If that were my dog, you'd see a gas problem there. But you can see that this person is leaving lots of particles and microbes in the room. And depending on the air management and the characteristics, there's communication between surfaces, the air environment. Depending on how tight your building is, there's more or less interaction between indoor and outdoor particles. So that's a great visual, I think, for helping us understand, our roommates, basically. And most of these organisms are good for us. We couldn't live without them. However, clearly not all of them are good for us, or we wouldn't be meeting virtually like we are right now. So this is a work out of the University of Oregon showing that each of us is like an ecosystem enclosed. We're about 70% bacteria by cell number. And we put these out into the indoor environment. And this part is fascinating. And this is what makes your work so incredibly valuable. Depending on how a building is designed, used, and ventilated, certain organisms are selected to survive, and certain ones will not survive indoors. And so clearly those indoor organisms are going to affect the health of occupants at the time and in the future. So if you think about the power of this, the indoor environment is now, we spend 90% of our time indoors. The indoor environment right now is the place that is governing which microbes survive and affect our health in both good and bad ways. So that's really, really powerful. So I'm going to show you a study. This is in a brand new hospital. This was done in 2014, 2015, where a group of microbiologists wanted to see how a brand new hospital, a LEED Silver hospital in the Chicago area, was populated by bacteria, viruses, fungal organisms called the microbiome. In this case, the microbiome of the building. So they took 10 patient rooms and 2 nurse stations, and over 13 months, they tracked those parameters that you can see, like every 5 to 30 minutes. So we had about 8 million room data points. So temperature, hand hygiene with an infrared beam break and a video monitor, pressurization, lighting, CO2, humidity, room traffic, both visitors and clinical staff, in and out of the patient rooms, room air changes and outdoor air. So again, a lot of data points. So I said, hey, I'd love to look at patient outcomes of all the people in those rooms over 13 months. So I had about actually 370 patients. And specifically, I was interested in these infections. So I was wondering, are there any indoor parameters that either protect or contribute to infections that people get while they're in the hospital? Surprisingly to me at the time, and this is before I knew anything about Condair or anything about anything that Condair does, our statistician came back saying that the most powerful correlation was between low relative humidity in the patient room, and that was correlated with a higher number of infections. And as the relative humidity, the average relative humidity in all the rooms were similar, as the average relative humidity went up over 40%, the nosocomial or healthcare associated infection rate went down to 0 in August. And this is statistically significant. So I thought, well, it's also seasonal, so they must have messed up and missed something else. So I was skeptical. We got another statistician who came back and said, look, this is an independent variable. This is not related to crowding. It's not related to the flu season. This is independent of other variables. So again, I was absolutely startled by this. Still skeptical. We started another study. This is in a nursing home. Right now, about 45% of the COVID-19 deaths are in nursing homes. So this is really important. So we looked at patient infections. This was before COVID-19. However, we're still doing this study now. So we were looking at respiratory infections, gastrointestinal, urinary tract, eye infections, and skin infections, and relating those or analyzing the incidence as that related to indoor and outdoor climatic factors. And once again, our data came back showing that when the indoor relative humidity was less than 40%, especially with GI and respiratory infections, both bacterial, like bacterial pneumonia or viral pneumonia, or sinus infections, when the relative humidity was less than 40%, the GI and respiratory infection rate was high. And the infection rate came down, and at between 40 and 60% indoor relative humidity, we had the all-time low of infections. This facility has humidified, and we've seen a leveling out, a very low rate of infections, and they've had no COVID-19 deaths. So those are great correlation studies. This study goes a little further because it has a parallel control. This study was done by the Mayo Clinic, by Jennifer Ryman's group. Half the school is humidified to 45%. Half was just left to do what happens in the wintertime in northern Minnesota. Bring in cold air, heat it up, relative humidity dropped. And you can see that in the humidified half of the school, the number of airborne particles, this was looking at influenza, the number of airborne particles carrying the flu virus was more than half the rate in the non-humidified part. Secondly, the actual activity or the infectivity of the influenza virus was much less in the humidified part of the school. And not surprisingly, consequently, there were many fewer children absent in the humidified part of the school. So this was one study. They've repeated it with 4 schools and have found the same trends. And this study is in the bibliography, so you can check out the paper. So let's just take a look. So here this person isn't wearing a mask and comes into your house or your office or your school or the hospital and is coughing. What can we do indoors to help prevent other people from getting sick? Well, you can glare at her for one thing. That's what happens where I live for not wearing a mask. But you can see here that some of the droplets coming out of her mouth are large and they fall rapidly to the ground within 3 to 6 feet. And for the longest time, the CDC and the World Health Organization was saying that COVID-19 or the SARS-CoV-2 virus was pretty much only spread by large droplets. And the rest of us were like, wait a minute. There's also data showing that the genetic material, the RNA, has been found, 14, 20, 25 feet away carried by these smaller droplets. So this paper came out, it said the world should face a reality because there's no black and white distinction between large droplets and small droplets. Large droplets evaporate in a dry environment and become tiny droplets. And we now know with newer testing techniques that even 0.5 micron droplets can be infectious. So let's think about these 3 stages. Where can we interrupt the transmission of this disease or any disease? So you can stop the person from coming into your house and coughing. That's not really an indoor air issue. We can diminish the transmission of the virus through the air or through surfaces. And is there any way we can actually impact the health or the vulnerability of other people by indoor air management? So let's take a look at the 2 stages, middle and to the right. So we now know from multiple studies that when the relative humidity indoors is less than 40%, you have greater aerosol transmission. It's much harder to clean the surfaces because there's recontamination from infectious particles falling out of the air. And thirdly, for reasons we don't fully understand, many bacteria and viruses are actually more infectious. Separate from the number of them, they're more infectious when the humidity is low. So again, I'm talking, you're breathing, droplets come out 100 microns in diameter. At 20% relative humidity, they desiccate within a fraction of a second to reach moisture equilibrium with the air and become what are known as droplet nuclei. And they've been found, hours, days, weeks later, not with COVID-19 per se, but those little droplets persist, and whatever they're carrying can persist. Furthermore, and again, this study is with influenza A. On the x-axis, you can see the relative humidity. When it's less than 40%, the influenza A virus is highly infectious. And when 40% is reached, 80% of the viruses are inactivated within 15 minutes. So 80% inactivated within 15 minutes. That's powerful. And with many viruses, you see a trough between 40 and 60%. In this study, we didn't see it come back up. But 40 to 60 is like a sweet spot for indoor relative humidity, where human health is optimized and virus pathogenicity is diminished. So that was influenza A. Here, looking at the coronavirus, you can see this is a log inactivation scale on the y-axis. You can see, and time on the x-axis, at indoor relative humidity, 20% at comfortable temperatures, you see kind of a steady persistence of infectivity. 80% of the green line, you see some inactivation, and actually it's a log scale, so you see quite a bit of inactivation. But look at 50%. At 50% RH with a comfortable temperature, you have rapid inactivation of the infectivity. And this is separate from the number of particles in the air. And it's not just microbes that are affected by indoor relative humidity. And I'm saying relative humidity, so all of those who are thinking, why doesn't she talk about absolute humidity or dew point? It actually is relative humidity that includes the temperature. That is the most important variable that dictates the vapor pressure. But you can argue with Glenn about that. But anyway, people also are affected by dry air. The average one of us in 20% RH becomes 1 to 1.5% dehydrated in 8 hours. It has effects on all of our body. But let's take a look at our respiratory tract, because that's what we're kind of focusing on in this, this moment in time. So this is a study out of Yale that was published a year ago in PNAS, which is an amazingly wonderful journal. Really tough to get published in. It's a Proceedings of the National Academy of Science. So this group out of Yale wanted to understand why dry ambient air is associated with, in this case, flu, much worse disease from influenza. You know, because at 50%, if you're exposed to that virus, you might not even get sick, you might get a little sick. But in the winter, when the indoor relative humidity is low, that's when we're kind of wiped out. Well, it ends up, and this, again, this study is in the bibliography, that all of the initial respiratory defense mechanisms that our body has are impaired at 20% RH. The mucus that lines our sinuses, our throat, our nose, all the way down into our lungs, that mucus layer in dry air becomes more viscous. It doesn't trap particles the way it's supposed to. The little hairs called cilia that exist from our throat down into our lungs, the cilia are supposed to wash upwards to keep particles away from our delicate lung tissue. The cilia can't operate even with a slight increase in mucus viscosity. And even more surprising, the other steps that our body has in the first response of our immune system, the other steps are impaired as well. Our cells don't manufacture interferon, which is protective. Other cells that would limit inflammation or clean up any tissue damage, those cells don't work as well. So at 20% relative humidity, all of these are impaired, and yet at 50%, they're optimal. We've known this for a while. This is the Sterling-Avondale chart that in 1985 pointed out this sweet spot of 40 to 60%, where infectious disease problems are minimized, allergies are decreased, ozone-related health impacts are decreased. So that's 1985. So fast forward. So I put my name on this. So using the same graphical format, taking the new testing technologies such as genetic analysis tools, computerized data mining for human health studies, we're still seeing this relative sweet spot, 40 to 60%, where human beings do the best and the bad microbes are inactivated, relatively speaking. And the good microbes, the ones that actually help us live and metabolize our food and that we really couldn't do without, they're optimized in this 40 to 60% sort of Goldilocks sweet spot. What do we do about this? You know, we now know that there are many different technologies for eradicating organisms in the air. You know, there's ultraviolet germicidal irradiation, there's ionic bipolarization, there are hydrogen peroxide misting, and all of these things have a place. But the only strategy that is both natural, so it doesn't create resistance, and decreases the number of infectious particles in the air, and it's the only thing that I know of that actually supports the health of all of us indoors. And this happens as soon as you're in the building. You don't have to wait for the air to go through the mechanical system to get cleaned or filtered. So it's really powerful. So in summary, this sweet spot, it accomplishes two things. It decreases the burden of infectious SARS-CoV-2, which causes COVID-19. So in shortening the long distance travel of particles, it optimizes the benefits of social distancing. It makes surface cleaning, hand hygiene more effective. And then again, and uniquely, it also supports the health of building occupants. And if you have dogs like I do, decreases static electricity so you can pet your dogs and not shock them, which is awesome. So I maintain that if we could effectively humidify our buildings, and I know in many climates this is not easy or cheap or instantaneous, but if we could, if I had a magic wand and we could humidify all of our indoor spaces, I think we could begin to turn around this alarming trend. So thank you very much. And Glenn, Louis is right behind me and he says hello.
Hi, Louis.
So take it away, Glenn.
Thank you very much, Stephanie. Dr. Taylor, that was a great presentation. Every time I watch your presentation, it's a little bit different. I always learn something every time I listen to you speak. It's great that you're doing those YouTube channel bits a few times a week on Condair's YouTube channel as well. So I encourage everybody to go and check that out as well. And also a little housekeeping note, we do have a section for questions, so you can go into the questions area and put some questions in there. I'm going to have Graham Holmes join us at the end of the presentation to help Dr. Taylor and I answer some questions. Graham is a very knowledgeable individual that is joining us today as well from Condair. And lastly, I'd like to continue on with the presentation, and I'm going to be talking a little bit about the solutions available to us today. So Dr. Taylor talked a lot about the problem, and now I think we all learned a lot from Dr. Taylor. So here are some of the solutions. Condair is a manufacturer of humidifiers and evaporative coolers, as well as dehumidifiers now. We've long since been able to help everybody in the Ontario market with steam generation. We've got electrode and resistive electric humidifiers, 2 types of gas humidifiers, and also we can use central plant steam in your building to humidify. A little bit less known, and we're trying to get the word out because we're really excited to have a really large selection of atomization and evaporation products. So anything from in-duct, media pad, high-pressure nozzle, our DL series, which I'm going to be talking about later, to a large assortment of in-room direct systems for manufacturing electronics, as well as a complete line of water treatment systems. We're really excited. We just got to watch this ourselves as agents. Condair has now got a desiccant dehumidifier or a desiccant dryer line, starting out with some smaller CFMs, but this is going to be a great little product, so we can now help on both ends of the spectrum with your humidity control issues. A little bit of technical background on the different types of products. Hopefully this helps everybody when you're talking about what technology you're going to be putting into your building next time. It's really important to understand the difference between isothermal and adiabatic. So isothermal, or steam, is what most of us are used to seeing, and that covers your gas humidifiers, electric humidifiers, process plant steam. And generally, we're using a fossil fuel gas electricity to boil water, very similar to boiling water in a pot. On the other hand, we can also humidify and also do evaporative cooling with adiabatic humidification systems. And literally, just like the waterfall, anytime you have water present, some of it is going to evaporate into the air. And when that happens, not only do you humidify the air, but you actually cool the surrounding air down. Many of you probably have gone to Canada's Wonderland and seen the cooling stations, and that's why that works. So hopefully that helps a little bit trying to understand the differences between the two. And you can really take advantage of the adiabatic technology and the cooling effect in buildings, like extending your economizer seasons, reducing chiller kilowatt consumption runtime. We have entire presentations on that as well. So very high level. Of course, the Nortec EL replaced the NHMC, and it is by far the easiest to maintain, most energy efficient, electrically efficient, and water efficient humidifier on the market. This is the replaceable cylinder unit. I think my dad likes to tell a story that Joe Nardi at Smith & Anderson helped him sell one of the first units back in the 70s. Unfortunately, my dad's not on the presentation today, but I'll leave it at that. We also now have the Nortec RS. The RS is a great product for labs. We've done a lot of labs with this unit. It's very good when you want to be able to maintain plus or minus 1% RH with the SSR solid state relay control in there. And we also have the scale management bucket on the bottom. Condair has really tried to address maintenance and making ease of maintenance a priority in all of their products. The gas humidifier line has been updated. We now have two styles of vertical upright models that take up less floor space. We have the high efficiency condensing series now, as well as a updated version of the medium temperature. And the high efficiency condensing one I really like because we can now use CPVC venting, which the installers really like. When it comes to in-duct adiabatic systems, we want to talk about sustainability a little bit here today and talk about the DL, which we're most excited about. In-duct adiabatic systems are becoming very popular because everybody's trying to reduce greenhouse gases and also save on the bottom line. There's a bunch of different systems, and we're seeing a lot of evaporators out there, whether it's the white polyester media that you see there from Condair or a fiberglass-based system. These systems don't require RO, so they have a lower capital cost, but the maintenance is a little bit higher, and you don't have the greatest control. When you go to the high pressure nozzles, everything is stainless. It's high pressure, so you have high, like 1,000 psi water to deal with special fittings, and also it's not very efficient with water consumption. If you spent a lot of money creating RO water, you really need to consider how you're using that RO water in your system. So that brings us to the DL. We're so excited about the DL because it answers everything. We really feel like it's well, a bit of a pun here, the silver bullet. It's the best of both worlds. You've got low pressure nozzles, which are like almost no maintenance, and you've got a ceramic plate that you never have to replace. It's there for the lifetime of the humidifier. The installation time would be the one setback for the DL. I mean, it is a little bit more on the installation, but once you have it installed, we've got very, very satisfied clients. An overview of the DL, you can see that we are providing everything from the beginning to the end of the installation. And we're also providing everything from the beginning to the end of the service life of the equipment. We can assist you with the selection of the equipment, the sale, the commissioning, recommissioning, and also we can come and do, through our partners at Condair, we can come and do bacteria testing on all of our humidification equipment, as well as help you with your service and maintenance and training. I should point out that you're looking at a couple things here. We've got the RO in the middle, as well as the hydraulic unit, which includes the silver ion dosing system. And inside the duct, with only 24 inches required between the nozzles and the ceramic, we've got the nozzles, the ceramic there, and all the lines are self-draining. So here's a closer image of the DL itself. You can see we've got everything here. This is sort of a setup of a picture that Condair had down at the AHR trade show, or what we all call ASHRAE down in the United States. I really want to point out here and just stop. And we've been talking to our friends on CSA for healthcare, and I know there are a few watching today, which is great. Thank you very much for joining us, everybody. CSA has had long-standing concerns about water in the air handler. And the two main concerns that we're aware of are both hygiene, water in the air handler, how are you going to handle that? And also maintenance. Are these systems really easy to maintain? And, if you're accessing an air handler, how much access do you have to have, and how much do you have to disrupt the airstream? Well, I'm really excited to announce the DL actually addresses both of these concerns, and we're going to continue to work hard with our friends at CSA to show them that the DL is the right solution for both reducing energy, saving hospitals money, and also keeping a high level of hygiene in the back of everybody's mind. A couple of things I'd like to point out at a really high level. I've talked about the low pressure nozzles here, so we don't have high pressure fittings to worry about. The ceramic media on the DL is a permanent, very porous ceramic media with a low air pressure drop. And it also requires a short installation section. If you compare that to a high pressure nozzle system, high pressure nozzle systems in the duct actually require many, many, many feet of air handler length if you're going to actually get any kind of level of efficient water evaporation. That's RO water that you've already used electricity to create, and you've already wasted a lot of water creating that RO in the first place. You really want to make sure that when you fog or spray RO water into the air, that's actually getting evaporated. So we have fantastic evaporation efficiencies with the DL above 85%, above 90 in most cases. This was my pun about the silver bullet. The adiabatic wet section hygiene of the DL is backed by the silver ion dosing system. So we're continuously dosing very safe levels of silver ions into the water. So anything that the water touches, none of it is aerosoled, but anything that the water touches, including the ceramic plates and the surrounding walls and the floors, are coated in a small amounts of silver ions, and the silver ions actually stop the bacteria and viruses from propagating. So this is a key part of the hygiene of the system, and that is also included in the overall system hygiene is obviously safe RO water treatment with UV, and also self-draining hoses. We don't want standing water anywhere, but everything has been thought of in the DL system to make it hygienic. Very, very key to the DL, and I think this is why you've seen so many hospitals in Europe adopting the DL, as well as hospitals in the United States now are putting DL systems in. This Fresenius hygiene certificate is a massive achievement for Condair. The DL humidifier as a whole system is the only system in the world to have this certificate from the Fresenius Institute. I encourage anybody after this presentation to go to the Fresenius Institute's website and just read up about how prestigious they are. They're probably the highest rated certification company in the world. When it comes, that's enough on the DL for now. I just wanted to point out that when you want to go do in-space humidification, we've also got your back with Adiabatic. We have a wide range of products that can put Adiabatic humidification right into your manufacturing or electronics operation. Anytime that you have heat being generated in the space by machines or lighting, it's a no-brainer to put a system like this into a facility. The incentives are massive. We had one customer that almost did a project for free. So please call us if you have any in-space applications. We have a very hygienic system with PLC control that'll really give the customer a sense that they've got something special and that's going to operate for a long time very well in their place. In conclusion, I've got a couple slides. Just wanted to point out again, when it comes to the problem Dr. Taylor showed us, we have to try to keep humidification up as high as we can. 40 to 60 is the obvious goal. But we're also, we're very concerned about the planet now. And so we also have to be concerned about the types of products that we use in our facilities. Luckily for me, as an agent of Condair, and I've always been excited to be able to say we have all of the technologies available to us, so we can help you with any technology that you want to implement. But as we move forward into greener approaches and thinking about the environment, we all need to start thinking more about adiabatic technologies. It's a greener approach. There's utility rebates. You can think about all the reduced energy consumption. And if you look at the chart, we sort of show, on the left side, you've got your fossil fuels, electric, gas, and you move through compressed air and high pressure systems. And right at the end is the adiabatic or evaporative media and the DL hybrid technology. It's the greenest technology on the end. I know that we'll probably get this question at the end, and again, I encourage people to enter questions now as we get to the end of our presentations. I've actually received a few by email and text, so thank you very much to those that sent them. Move on to the next slide, sorry. And the last one, just to show operating costs, we really do mean with the DL, the third from the right, it's silver. We want to looking at the operating costs for 1 year. When you compare the last two, the electric and last two electric, to operating an adiabatic system, the overall operating costs for the DL are the lowest amongst all the technologies that we offer. And that again comes back to those ceramic media plates and the low pressure nozzles. There's really not a lot to do in the airstream to do for maintenance. So that brings us to sort of the end of the formal part of the presentation. I'm going to also introduce at this point my friend Graham Holmes from Condair to join us on the line. We do have a couple questions that we've received by text here, and Graham, do you want to list a couple of them?
Yeah. Hi, Glenn. Thanks for bringing me on here, and good morning, everyone, or almost good afternoon. Hi, Stephanie, as well. So we've got a couple questions here from the audience. Two for Dr. Taylor immediately. So the first one, Stephanie, you've said that relative humidity has been identified as a key factor in preventing infections. Is there enough research to comment on the interaction of relative humidity with temperature? So specifically within ASHRAE's recommended range of 20 Celsius to 27 Celsius. So I think that equals out to about 70 Fahrenheit to about 80. In addition to that, many operating rooms are held at 65 Fahrenheit a lot of the time because the surgeons are garbed up so much, they like to keep it cooler. Does that have an effect on this as well?
So yeah, so the studies that are particularly relevant around humidification are definitely in the temperature zone where humans can occupy the space. So whether it's 60 degrees or even lower, 50 degrees up to 100 degrees, that's the range of the temperature in the studies that I've quoted you. You know, there are other studies that talk about like absolute zero, and I don't think there's any humidity, absolute zero. So everything I've cited is within the human occupied temperature zone. But you're right, Graham, in operating rooms, which can often be very cool because of the multiple layers of gowns, ASHI diminished the allowable relative humidity to 20% because we didn't at that time know how important it is to maintain 40%. Well, we did, but we didn't. So now we're working with ASHI to bring that back up to 40%.
Yeah.
Did that
and for
answer
those,
that?
Yeah, for those who don't know, ASHI is the American Society of Healthcare Engineers.
Yeah.
I think I got that right, Steph?
Yep.
A little interesting tidbit on the
if you do get sick, go into the sterile supply area because they humidify that to 35% to keep the masking tape adhered to the blue paper to keep your instruments clean. So at least we humidify for masking tape. Now we have to begin to do it for humans.
Do we have any other questions?
Oh, yeah. So in that same realm, Stephanie, does relative humidity versus absolute humidity, which one is really more important between the two? Like, for instance, when at the high or low range of the ASHRAE temperature recommendations, is there any benefit or issue if the RH is held constant? So if we hold the relative humidity to 40%, but the temperature lowers, the absolute humidity in the room is going to change. Where does that kind of play into all of this?
So, I mean, that's a question that I get a lot, and I resist answering because it involves a psychrometric chart. But it really is the relative humidity measurement that speaks to the evaporative forces that are detrimental to the human body. So, again, Glenn, or I would turn to you to discuss absolute versus relative humidity. But in the studies, we have found that it's the relative humidity that matters. So, again, I cannot speak in a very articulate manner about the psychrometric chart. So Glenn, can you answer that?
I'd say I'd be very happy to, if anybody's interested, I'd be very happy to do a private presentation for your companies, and we can get a little bit more in depth and bring out the psychrometric chart. I purposely deleted the psychrometric chart slides from today's presentation. I was trying to keep the focus on Dr. Taylor's excellent presentation, and that was really the message today. But absolutely, I'm with Dr. Taylor. Everything I've ever read from Sterling's chart to today, and all the wonderful stuff you're sharing on your LinkedIn as well. It's all our relative humidity. A little bit anecdotal. We also do a lot of dehumidification at Kilmer Environmental, and it's interesting. One aspect of operating room temperature and humidity control is at the other end, and talking about dehumidification and cooling. A lot of hospitals probably won't admit it, but if you're operating your air handlers with chilled water coils and you don't have a dual path airstream, you're probably struggling on the hottest, most humid days to maintain humidity in the ORs. And a lot of systems are designed right at the limits. You know, you're designing your temperature close to room temperature, 21 degrees, 70 degrees, 72 degrees, and right at 60% RH, and you can show on paper that your air handling system can handle that. But as soon as and this is where Dr. Taylor might want to jump in again, as soon as a surgeon puts on a full garb and gloves and mask and everything and walks into an operating room, they immediately want to go over to the wall and start going down, 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 down on the thermostat because they're hot and they're sweating underneath the garb. And that's where the difference between relative humidity and absolute humidity really comes into play, because you set up the room the way you want to at room temperature and 60% RH or just a bit lower. But as soon as the doctor or anybody goes and lowers the temperature, you haven't done anything to the absolute humidity, the absolute amount of humidity in the room, but just lowering that temperature now is going to increase the humidity in that OR above 60%, and now your OR is not safe to operate, and you got to close the OR down.
Yeah,
Right.
and that's absolutely true. And if you look at the studies around using, outdoor climatic factors to begin to tease out temperature and humidity, we're seeing an increase in contact, so direct contact transmission over 60%. And with many organisms, you lose that protective zone. The infectivity in general goes back up. And another component that's separate from relative humidity is that temperatures, below 65 degrees actually impair the initial healing process of cells. So if you've had surgery, last thing you want is while your skin is broken, is cut, you don't want those cells beginning to die from cold temperatures. So operating rooms are really not managed for patients right now.
Yeah. And, speaking of the temperature there, Andrew, I'm sorry if I didn't get your question exactly correct. I'm kind of mixing a couple of them that are similar together. So Andrew's asking if the temperature has any real impact, and you just mentioned below 65% does reduce wound healing. Are there any other effects from a lower temperature or higher temperature for that?
Well, again, for the aspects that we're talking about, supporting your immune system, decreasing the pathogenicity of bacteria and viruses, and removing particles from the airborne environment, it's really the relative humidity. I mean, there are plenty of other physiological changes, higher and lower. I don't know if anyone has Raynaud's syndrome, where your blood vessels get constricted at lower temperatures. So the body does respond to high and low temperatures, but the important parameter around your immune system and airborne particles is really the relative humidity.
Before we get to the next question, Graham, we've got about 5 minutes left here, and we have a second poll for everybody. The first poll, I'm gonna run it here, Graham, because I know how to launch it now. I'm going to be one of your best tools going forward. I promise. I know how to use the system. So we have another poll for everybody. I'm going to launch it now. If everybody could click on this quickly. We'll leave it open for 20 or 30 seconds. We're collecting responses.
We can keep answering questions as they go ahead.
Right, let's leave it. Sorry, Grant.
Yeah. So I've got a couple more questions here. The virus inactivation chart that you showed, Stephanie, I believe it's the one from Dr. Hugentobler, the logarithmic chart. It showed about 10% of viruses remain viable after 7 days at 20% relative humidity. Regarding the content of the chart, is the subject generic to viruses? Many sources suggest that SARS-CoV-2 virus doesn't last more than 2 to 3 days. As a member of ASHRAE Pandemic Committee, does Dr. Taylor have any other information?
So that chart really speaks to coronaviruses in general, but does this relative humidity inactivation impact apply to all viruses? No. There are two general categories of viruses called the enveloped and the non-enveloped. And for example, polio is one of the non-enveloped viruses. And non-enveloped viruses, and there aren't too many of them, actually do better over 50% RH. So in terms of the activity, the viruses that we see that cause most respiratory diseases are the envelope, the lipid enveloped ones that are inactivated. So as a member of the pandemic force, so ASHRAE, if you read the new infectious aerosol position document, it will address the issues of humidification that we've been talking about. ASHRAE is conservative, so it balances out known issues with the building envelope, condensation, the risk of mold, things like that. But there is documentation in the epidemic task force about this.
Okay, I got two more, so hopefully we got time for it. First of all, from Robert, can you talk about the feasibility analysis for energy savings? Do you have a case study that will illustrate the energy savings? So I think this is directed more towards the different type of humidifier technologies. At Condair, we do have an energy analysis tool that we use to take your exact building, your exact location, what kind of heating and cooling technologies you're using in your space, and really give you a $1-year dollar operating cost for all of our units. So that includes anything from electricity to gas to water usage, all included. The quick slide that I think Glenn showed is based only on the actual energy use, so gas and electricity. So that's why the DL is so low on the actual energy usage, and where the dollar value also incorporates the water usage, which is usually pretty standard between a lot of our units because they're all use water anyways. So it's really just the energy analysis from Glenn's slide, and for that dollar slide, it shows the total operating cost. Anything to add there, Glenn?
No. We've got about 1 minute, Graham, so I can close the poll in a second. Do we have another question that you wanted to pick out?
Yeah, so I got one more here. It talks about the latest addendum to ASHRAE's position document. It doesn't state that ASHRAE actually recommends 40 to 60%. It simply shows you the research, and stated as such, organizations take it as not being a regulation and not necessarily a fact, but it's kind of a holistic approach. Stephanie, do you know why ASHRAE hasn't made this an official recommendation yet? Or can you comment on the infectious aerosol position document?
Yeah, so if you compare the 2014 position document to this one, you'll see relative humidity mentioned, like, I don't know, 15 times versus 1 time in the previous one. So the specific range, 40 to 60%, was in the text up until the last editing committee meeting, which I'm not a part of. And I guess there was one person who was very concerned about people adhering to that level regardless of outdoor temperatures, having condensation issues. So they took that range out at the very last minute and said again and again, to manage the humidity based on the infectious particle of concern. So you're right, they do tiptoe around recommending 40 to 60%. It was accepted by our committee until that very last session, closed door session. Only a couple people were in.
On Condair's YouTube page, I have an episode as well going over that position document and comparing it to the 2014 and the previous years as well.
Great, yeah.
Okay. Any other questions, Graham?
That covers it all.
Okay, we still got most people here. It's interesting, if everybody's interested in the second poll, are your clients asking or inquiring more about humidity since the outbreak of COVID-19? It was pretty close to 50-50, slightly more than 53% that voted are saying no. So it looks like we've got to do this webinar again next week. But
One last comment, Glenn, from Mark. He's wondering if they can get a copy of the latest ASHRAE aerosol document. It is available online at ASHRAE, but we'll make sure to provide a link in the follow-up email from this session that will be sent out to all attendees.
Thanks, Graham. And our slides too.
You're welcome to have my presentation.
Perfect.
Glenn, you
yeah.
Okay, well,
All right.
thank you, Graham. Thank you very much, Dr. Taylor. It's been wonderful. This is my first time working with you on a presentation directly, so I really enjoyed it. It's great to hear a new take on things. And make sure to say hi to Luigi for me.
I will. Thank you all. Thank you, Glenn and Condair and all the attendees.
Thanks everyone for joining us.
Take care.
Bye-bye.